In the mid-20th century, the moon was a geopolitical finish line. The objective was to plant a flag, collect surface samples, and return home. Today, the global space economy is transitioning from scientific exploration toward industrial extraction and the active development of cislunar infrastructure. This shift is driven by the need to secure critical resources that can break terrestrial supply chain bottlenecks in advanced computing and clean energy. Two distinct factors are making off-world extraction technically viable. Reusable launch vehicle architectures are driving down the cost to reach orbit, while autonomous robotics are scaling to manage complex tasks in the lunar environment. While commercial-scale lunar supply lines are not expected to yield sustained volume before the early 2030s, the foundational architecture is being built today. Sovereign space agencies are deploying capital for base camps, and aerospace startups are already signing multi-million-dollar forward purchase agreements for lunar isotopes. The moon serves as the starting point for a highly capitalized, multi-trillion-dollar industrial supply chain. Every calculation in off-world economics is dictated by the immense energy required to escape Earth's massive gravity well. Delivering a single kilogram of payload to the lunar surface still costs tens of thousands of dollars. Because of this cost, the business case for lunar extraction is split into two entirely distinct operational models. The first model targets materials with extreme terrestrial scarcity and high value-to-mass ratios. For these resources, the logistical cost of a 480,000-kilometer round trip back to Earth is economically justified. The second model focuses on bulk resources like water and structural oxides. These materials are inexpensive on Earth. Launching them out of the atmosphere is cost-prohibitive. They must be extracted locally on the moon to be viable. The end users are different for each. The first model exports specific isotopes to terrestrial technology sectors, while the second model serves in-space operations, providing the propellants and habitats needed for deep space logistics. Mastering both models is the mandatory prerequisite for establishing a permanent human footprint outside of low Earth orbit. Helium-3 is the most immediately lucrative export commodity in the lunar resource portfolio. This stable, non-radioactive isotope is exceptionally rare on Earth, but exists in quantities exceeding 1 million metric tons within the upper layers of the lunar regolith. Scarcity drives the price to $2,500 per liter, or $20 million per kilogram. Supply is capped as a decay byproduct from weapon stockpiles. Yet demand is forecast to expand 14-fold by 2035, driven primarily by the 58% allocated to the quantum computing industry. Superconducting quantum computers require environments near absolute zero to prevent heat from destroying quantum states. To reach these temperatures, dilution refrigerators utilize the phase separation of a helium-3 and helium-4 mixture, cooling systems to 7 millikelvins. Startups like Interloon have secured forward purchase agreements worth hundreds of millions of dollars with major cryogenic manufacturers, guaranteeing future deliveries of lunar helium-3. Autonomous harvesters must excavate the regolith, heat it to desorb volatiles, and isolate helium-3 for Earth return. Controlling the cislunar supply of helium-3 will provide direct influence over the trajectory of next-generation encryption, drug discovery, and national security infrastructure. The second economic model is in situ resource utilization, or ISRU. It targets processing raw materials that remain in space to support ongoing missions. The foundational resource is water ice. Massive concentrations are trapped inside deep, permanently shadowed polar craters that haven't seen sunlight in billions of years. Extracting this ice through low-power microwave heating allows for the local production of liquid hydrogen and liquid oxygen. Through electrolysis, water becomes Hydrolox rocket propellant. This is the gear ratio of spaceflight. Manufacturing 1 kilogram of propellant on the lunar surface saves launching roughly 10 kilograms of mass from Earth's surface. Beyond water, the dry lunar regolith is rich in oxides that can be processed to yield both breathable air and industrial metals. Through carbothermal reduction, ilmenite is heated to 1600 degrees Celsius in the presence of methane. This process separates the oxygen from the metal, leaving behind iron, silicon, and titanium slag for local manufacturing. Successful ISRU establishes the lunar surface as a self-sustaining cislunar gas station and heavy manufacturing foundry. The transition from theoretical ISRU to operational extraction presents severe engineering hurdles due to the cryogenic vacuum environment. Machinery must penetrate rock-hard, ice-bearing subsurface layers without generating enough friction heat to vaporize and lose the volatile materials. The Trident drill is the primary tool for subsurface prospecting. By taking 10-centimeter bites at 120 RPM, it limits its power draw to 87 watts, maintaining the thermal stability of the ice samples as they are brought to the surface. The primary bottleneck to scaling the lunar economy is energy. The lunar night lasts 14 Earth days, with temperatures at the poles reaching -418 degrees Fahrenheit. Solar power alone is insufficient for continuous mining. Standard and vertical arrays cannot provide the high-density energy required for heavy industrial processing during the long lunar night. The deployment of modular fission surface power reactors by 2030 is the requirement for scaling this industry. Without continuous high-density baseline nuclear power, the commercial architectures for lunar extraction will remain unfeasible. The rapid iteration of commercial extraction hardware is moving faster than the international legal frameworks governing space. The 1967 Outer Space Treaty established that celestial bodies are not subject to national appropriation. Article 2 explicitly prohibits claiming sovereignty over the lunar surface. To bypass this legal standstill, the US and Japan have passed domestic laws recognizing animus possidendi, possession with the intention to own. This allows private entities to own resources they have physically separated from the lunar surface. This legal framework supports the US-led Artemis Accords. The model relies on a decentralized ecosystem where sovereign agencies act as anchor tenants for commercial extractors. China is pursuing a centralized parallel architecture through its International Lunar Research Station. Their Chang'e missions have already achieved historic far-side landings and returned samples containing rare earth phosphate minerals. The divergence between these two architectures raises the risk of regulatory conflict over the ice-rich craters of the lunar South Pole. The industry is currently transitioning from technology demonstration into aggressive orbital prospecting, targeting operational extraction pathways by 2035. This progress is driven by massive sovereign basecamp investments, venture capital inflows, and hundreds of millions of dollars in binding commercial offtake agreements. The stakes are high. Securing helium-3 dictates technological supremacy in computing, while ISRU water ice determines the speed of multiplanetary expansion. As the physical infrastructure grows, the global community must establish binding international deconfliction mechanisms before competing blocks land heavy hardware in the same polar craters. The industrialization of the moon is the cornerstone of the 21st century supply chain, and the architecture being built today will dictate the future of Earth and deep space.